This is our last lecture, part 2 of timber design, where I will introduce you on the design for flexure member. In order for you to design the flexure member, first you need to check for the geometrical properties of the timber given, and then determine the K factors, and then the grade stress. Right, and then the check for permissible bending stress, and lastly to check the maximum bending moment. Permissible stress in timber are governed by the condition of service and loading. Okay, it's given by this formula: permissible stress equals to grade stress times the modification factors. Okay, modification factors is K value. This is the first K value called as a duration of loading, K1. It can be seen in table 5 where it should be multiplied for various duration of loading. For example, we have a long term. Long term is consists of a dead plus the permanent load. So the value of K1 is 1. For medium term, consists of dead and temporary imposed equals to 1.25 of K1. And short term is dead plus impost and plus wind. So equals to 1.5, and very short term is dead plus impost plus wind is equals to 1.75. Then load sharing system K2. Okay, the load sharing system consists of 4 or more members such as rafter, joist, trusses or wall stud. So if member has a 3 and below, so there's no load sharing system. And this load sharing system should be spaced at the maximum of 610 center to center. And the preferred grade stress should be multiplied by the load sharing system. So the value of load sharing system K2 is equals to 1.1. The limiting flexural stresses. So the actual maximum flexural stresses should be lesser or equals to the permissible flexural stress. Okay, the meaning of this line is parallel to the grain. Design the flexure member, it should be not that all the lambda m ADM. Okay, lambda m ADM is the permissible flexural stress determined by multiply the grade stress lambda mg times the K factors. The lambda mg, the grade flexural stress, can be seen in the clause 7. You can go through there. For individual hardwood and softwood, and therefore the timber flexure member is capable of sustaining bending stress safely if the following condition is met. So the maximum should be lesser than the allowable grade flexural stress times with the K1, K2, K5 and K6. Okay, then K3 is the length and position of bearing. So the bearing must have 150 mm or more. So the bearing should be, if your bearing less than 150, located at 75. So you can see at the figure 1 and multiply with the modification factor given in table 10. Okay, this is the position of bearing. This is the bearing less than 150, and this is the end of the flexure member where the location is 75 mm or more. Okay, in table 10 of Malaysian Standard Modification Factor K3, if the length of bearing in mm is 10 mm, so the K3 is equals to 1.74. So you can see all of these values for each of the length bearing. Okay, for 150 or more, so should be 1. Okay, this is the effective span. Effective span should be taken as the distance between the center to center bearing. And given by this figure, okay, this is the support, okay. And this is the beam, okay, while the clear span is from the faces of the support, The effective span is center of the support, center to center, and the total span is actually the total length of the beam. And if we have a shear at notched ends K4, so the square cornered notched end flexure should be determined as follows. For notch at the top edge, you can determine by using this formula. And for notch at the undersides is this formula. So the H is the total depth of the beam and A is shown in figure 2. The HE should be not less than 0.6 H. This is the figure of notched beams. The HE is the effective depth of the beam, and the beam with notch on the side, and this beam with notch on the top edge. And then K5 form factor. Grade bending apply for member solid or rectangular. So cross section. For other shape, the grade size should be multiplied by the modification factor K5. For solid circular section, K5 is equals to 1.18. For solid square section is 1.41. For others is equals to 1. Then K factor of depth factor K6. The grade bending stress given in table 1, 2 and 4 apply to material having depth of H up to 300 mm. And for beam greater than 300 mm, the bending stress should be multiplied by the depth modification given by this formula. For solid and glued laminated beam, for depth less than 300, so you just can take the K6 value is equals to 1. And then you check for deflection and stiffness. The flexion member preloaded should not exceed 0.003 of the span. For domestic floor joist, deflection under full load should not exceed 0.003 times the span or 14 meter, whichever is lesser. The 14 mm deflection is to avoid undue vibration under moving impact. So the deflection of actual should not be should less than or equals to the permissible deflection. So the permissible deflection is equals to 0.03 times span or lesser of 0.003 times span or 14 mm. And this is also can be checked for the shear deflection. Okay, but I will not explain further. This is only for your own knowledge. And continuation from previous slide, you can read through. And the lateral support for ensure that solid and laminated beams of rectangular do not experience lateral torsional buckling. So this is the limiting by depth to breadth ratio, D over B for the actual should less or equals to D over B allowable. So depth to breadth ratio is given by this table. The maximum depth to breadth ratio. If it's no lateral support, so maximum depth breadth ratio is 2. Ends held in position. So it's 3. And check for others. So the value is this. Okay, then we go for example. This is where you need to determine the permissible bending stress parallel to the grain and the magnitude maximum bending moment for a beam, main beam. And this is the parameter where the interior beam with smooth surface. Second parameter is nominal size is 50 times 200 mm. Is under categorized couple species with standard grade. Has a long-term duration of loading where no load shear. Okay, check for the numerical properties of nominal size 50 times 200. You can go to Malaysian Standard Part 2 Table B4. The depth is h, the b is the breadth of section, and section of modulus is given by b times h square divided by 6, so equals to this. And then determine each of these k factors, k1 until k6. Okay, the value of k1, we know that it's a long term with only dead and imposed load. Thus, the value of k1 is equals to 1. Okay, the parameter also load sharing, but this example has no load sharing, so it's k2 is equals to 1. And then length of bearing, because it is has more than 150 mm of length of bearing, there's the k3 is equals to 1. So the k factor k4 shear notch at end, so the k4 is for a notch on top edge is equals to 1 because the A value is more than the effective depth. And form factor K5 because it's rectangular, so it's equals to 1. So K6 depth of factor because the depth is less than 300 mm, thus the K6 is equals to 1. Alright, so here we have a summarize all the value of K factors for this example. So we have all the K1, K2, K5 and K6. Whereas K3 and K4 no need because the parameter is not there. So we have only 4 K factors here. So check for the grade stress for Malaysian Standard Part 2 Table 1 for grade, for wet grade. And Malaysian Standard Part 2 Table 2 for dry grade. And we have a couple species standard grade, and check the parameters from these tables. So we can see the bending parallel to drain is equals to 17.3 Newton per mm. Okay, you need to check the table 1. And permissible bending parallel to drain, STD, standard grade is STD, check for the STD. Those permissible bending parallel to drain is permissible equals to the grade stresses times the K factors, and 17.3 this will times all the value of K factors, so it equals to 7.3 Newton per mm square. And calculate the maximum bending moment. So the permissible bending is equals to the maximum moment divided by the ZXX. So MFX is the permissible times the value of ZXX. So we can get the value of maximum moment equals to 4.69 kilonewton mm. Okay guys, thank you. That's all.